Dealing with analytical databases is an essential skill for data scientists, data engineers, and data analysts. You need to design and query databases that help you extract valuable insights from data. But why do we use different techniques to model transactional databases versus analytical databases? Hey folks, I'm Trent. I've been a professional data engineer for 5 years, and in today's video I wanted to answer a question I had when I first started my career. Why do we need analytical data modeling? If you've studied databases in university or done a course on databasing, you've probably come across third normal form and thought that's all there was to modeling data. But when it comes to analytical processing, dimensional and other modeling techniques turn out to be much more effective approaches. In this video, we'll explore the why, what, and how of analytical data modeling, and specifically go through dimensional modeling as a technique. And by the end, you'll see how this can help you extract valuable insights from your data. Let's jump right into it. The first question we need to answer is, why is data analysis important in the first place? Well, it turns out that there's a lot of data out there. And this is an image showing the amount of data collected in an internet minute. This was taken in 2021, so this has probably gotten bigger by now. And you can see things like 3.8 million Google search queries happen every internet minute. About 700,000 hours of Netflix are being watched every minute on the internet. So why do we care about this? Well, data has grown not only in size, but also in its power. We can start with measurement or looking at basic statistics. This is kind of a first level of maturity of data analysis. Effectively, you can think about measuring things like how many sales you have in a particular month and looking at things at how many customers you have. Then you can move on to discovery, where you can look at trends in your data. Perhaps you notice that your sales increase around December time because people are Christmas shopping. And then lastly, you can predict on top of that data. This is kind of a third level of maturity of data analysis, where you are really looking into the future with data and using techniques like machine learning and all of those fancy data science type techniques to predict the future. So this would be like predicting sales for the next month or looking at different customer types in your data sets. Now, to collect all the data we need to get through these levels of maturity of analysis, there was a rapid evolution of databases throughout time. Way back when, in the 1960s, hierarchical databases were first developed. I personally have never seen a hierarchical database, but these are pretty old and were kind of the first databases that existed, or databases in the form that we know them. Then in the 1970s, Edgar Codd proposed the relational database model, and effectively SQL is born at this stage. In the 80s, SQL would rapidly gain popularity, and companies like IBM, Microsoft, and Oracle would release their own proprietary SQL databases. Then in the 1990s, there was the rise of analytical databases and analytical database structures as well. So products like Informatica and Cognos were born. By today's standard, these are quite old and outdated, but at the time, these were really impressive to do analysis type work on top of. Then in the 2000s, we had the advent of kind of big data. Doug Cutting and Google introduced Bigtable and MapReduce to the world. And you've probably come across Hadoop, the Hadoop ecosystem if you work in data to manage big data. This really picked up traction in the 2010s. Tools like Hadoop, Spark, and cloud data warehouses became more mainstream. Throughout this time, you also had AWS releasing products like Redshift to help you with big data. And now in the 2020s, we've gotten vector databases to fuel our large language models like ChatGPT or Claude. The real question is, why did we need all of this? I mean, having one database is enough, right? So I want you to think through, why would you need more than one type of database? And further, why would you need more than one database in general? Like, why wouldn't a company just have a single database where they keep all their data, keep things simple, and just have that one database managing everything? Well, you've probably come across a few problems or thought through a few problems that could happen. One of them being concurrent access, right? Many people and many applications interacting with one database will quickly become problematic, right? And you'd have significant downtime. You could have hundreds of thousands of queries happening on a single database, and this could bring it down completely. This leads to problem 2, which is fault tolerance, right? You want to have replicas of your database ready to go because one database could fail and you need to be up and running as quickly as possible. So this can be dealt with by having replicas or having many replicas of a single database to come into action when anything goes wrong. Then problem 3 is performance as well. Compute gets expensive and you need to balance cost and benefit. So when you are dealing with just one type of database or you have one type of database, it may not necessarily be the most performant option. And specifically, it may not be the most performant option for your use case. This leads me on to ease of use. So this is really where things get interesting. Your use case may have great difficulty in using the type of database in question. If you think about it, there are databases out there like MongoDB, which are not relational databases. Why would people use those instead of using, say, Postgres? Well, it turns out that MongoDB is really easy to use if you're working with an object-oriented programming language, and you can kind of just dump your objects into Mongo and retrieve them out of Mongo just like that. So that's an example of where a use case would determine what type of database you're using. Really, for the rest of this presentation, I'm going to focus on this ease of use problem over here, as well as a little bit of the performance problem. The first two problems of concurrent access and fault tolerance are topics on their own. We can get into discussions about like replication in data and having the kind of leader-follower pattern when you have a cluster of databases instead of a single database, but that deserves its own discussion. Really, we're going to focus on problems 3 and 4, or at least these problems are the ones that we want to resolve with analytical data modeling. With that in mind, the core concept that I want to bring up is OLTP versus OLAP. So OLTP stands for online transactional processing, whereas OLAP stands for online analytical processing. So online transactional processing really just deals with real-time state, while online analytical processing deals with historic state. We can say that pretty broadly. Really, the core idea is transactional integrity. So when we're talking about an OLTP database, it needs to preserve transactional integrity. And effectively, that's handling frequent, low-volume, real-time events consistently. Typically, this is like an app that manages the data flow in real time. So you'd have some sort of production application over here, which manages operations on top of a database over here. And the database is effectively tracking state of the data in real time. You can think of this like a banking transaction, for example. When someone pays somebody else, you want the transaction to debit the payer and credit the beneficiary all in one go. And you want this to happen effectively in real time. You don't want this weird state in between where someone has had money deducted, but no one's had the money received, right? You could think of some really interesting states that could happen if that type of integrity wasn't guaranteed, right? Now, we contrast this to analytical integrity. And analytical integrity means handling infrequent, high data volume events consistently over a longer period. So typically the use case here is that reports are generated at some frequency, for example, daily, or an analyst is querying the database ad hoc or querying the data ad hoc. So this is handling large volumes of data over time and happening at either a certain frequency or ad hoc, but really the key point is that we're dealing with a lot of data, but at a lower frequency than a transactional database. And so analytical integrity needs to preserve data across history or historic states of the data. With this in mind, let's take a quick review of third normal form databases. Now, third normal form databases are kind of the de facto standard for online transactional processing databases. So these preserve transactional integrity. Just to go over the rules for the different normal forms of a database as a reminder, or if you haven't come across this terminology before, I'll just give a brief description of these. So for a database to be in first normal form, or a data model to be in first normal form, the data must be in tabular format, where each column contains atomic or indivisible values. So basically you can't put like arrays or lists or anything as elements in your data or on a table in a database, right? You'd expect it to have single values per element in your different tables. Then we can move on to second normal form. Now, the idea with moving through normal forms is that we need to be in the previous normal form in order to move into the next normal form. All I'm saying is that for us to be in second normal form, we need to assume or have done first normal form already. So this must already be guaranteed. And then all non-key attributes, columns that are not part of your primary key, must depend entirely on the primary key. Right, and then finally, there is third normal form. There should be no transitive dependencies, or non-key attributes must not depend on other non-key attributes. Now, this is a bit abstract, so we'll go through a bit of an example to illustrate this, but these are the rules for the normal forms. So as an example, imagine you're modeling a simple database for an online retail store. Imagine you get data of this form. You have orders, customers, their first name, customer address, product ID, product name, and the quantity that was ordered. Well, to start things off, this model is in first normal form. It only has atomic data in the table, so we don't have any weird lists or anything like that in our data. But this breaks second normal form. So for example, first name and address depend on customer ID, so this value depends on the customer ID, but not on the order ID or product ID, these are also primary keys in our table over here, and the first name of a customer is not dependent on them. So this breaks that rule of second normal form. Then further, it breaks third normal form as well. So for example, product name depends on product ID, so this product name depends on this ID over here, but not directly on the other key of order ID, right? This is not direct, or the product name is not directly dependent on which order it appears in, but this forms a transitive dependency, i.e. product name implies product ID, which then implies order ID. It's not a direct relationship, so this breaks third normal form. So to resolve this, you would go through the steps of breaking apart this table into a more consistent data model with the third normal form rules. So it would look something like this. Effectively, going through the process of normalizing our data, we would end up with a model that looks like this. And in it, we have customers separate from products, separate from customer addresses, which are also separate from sales orders and sales order items. Now, as a quick review of the notation used in databasing, if we look at the relationships between these different entities, we have customers to customer addresses. If we read the notation or the relationship between these two, marked by putting the primary key of customers or the identifier for customers into the customer address table as a foreign key, you can read this as customers have one or many addresses, and that's true. A customer can have a single address or multiple addresses, but a customer address, reading it back to customers, can have one and only one customer. Now, that's a pretty hard assumption to make, right? Technically, you could have two customers staying at the same address, but for simplicity's sake, I'm assuming that. And we can look at all the other relationships as well between our different tables. An interesting one is also like our sales orders over here. So this is kind of like a kind of invoice total of an order. And in here, we've got a relationship between sales orders and sales order items. If we read that relationship, we can see that order ID is injected as a foreign key over here. Notice that I've made a mistake. This indicator over here, or this crow's foot over here, needs to be put next to order ID, but you get the idea. So sales orders have one or many sales order items, but sales order items can have one and only one sales order. So that's just a quick reminder of how to read one of these ERDs if you haven't come across these before. But effectively, our model over here is in third normal form. So great, an application can easily update this with new sales, new products in real time. It avoids weird anomalies where if I needed to update a product in our flat denormalized table, well, I'd have to enter in a bunch of nulls in the customer information. So just going back a slide over here, if I needed to add a new product over here, and no one had bought it yet, you could imagine I'd have to have a null value over here, a null value over here, and things would get messy really quickly. So our 3NF or third normal form database really satisfies that need of being able to make updates in an easy and convenient way from an application. Now that's all good for our kind of front end application. You could imagine like our storefront or website on top of our online retail store was interacting with this database. The thing is, what happens if a sales manager asks us an analytical question? They ask us something like, which products are the most popular per city? And that's a fair enough question, right? And something interesting to know. So if you want to take a minute and pause the video, think about how you would answer that question using this data model. And you can assume that when we say most popular, we mean has the highest kind of number of sales per city. But the real point is, how would we bring together the data using SQL or a similar kind of like pseudocode language to answer this question? So take a second to think through that. Well, to answer the question, we could write a query, right? And query our data model. So effectively, we would select our city, product, and quantity over here, or sum total quantity, then also get a total value, so quantity times price over here, and select this from our sales order items, join this to sales orders, join this to products, join this to addresses to kind of get the city information, then do a group by city and product, and then perhaps order that by city and total sales. So great, we get an answer, but we had to do 3 joins, right? Which is a little inconvenient. We have to go through 3 separate joins, and it's a little hard to navigate through the database to answer this type of question. But what would happen if a significant number of customers move from Cape Town to Johannesburg? So this is an example from my home country, South Africa. And if you don't know, Cape Town is a coastal town, whereas Joburg, where I'm from, is a kind of landlocked city, right? We're in a province that has no coastline on it. So thinking through this, if many of our customers moved from Cape Town to Johannesburg, we'd obviously want to update their addresses, or they would update their addresses, their delivery addresses. If we go back to our model over here, a certain customer would then go and update their address lines. They would say that their city is no longer Cape Town, but it is now Johannesburg. And you would go ahead, do an update, and that would be easy to do on top of this model. The problem is that if we try and answer our question again, or if we try and answer our question before a whole bunch of our customers migrate from Cape Town, we would probably get a result like this. We'd have our city, product, quantity, and total. So the city being Cape Town over here, and perhaps the most popular product, or one of the products that sells really well, is a surfboard. That's what I assume that people from Cape Town do a lot. They kind of just surf. I don't know a lot of people from Cape Town. And we've sold 100 of these, and we've got a total value over here of like 100,000. You could imagine that as like $100,000 or rand, whatever currency you want to imagine this in. In Johannesburg, we need to have fun too. Our favorite product, or one of the products we buy a lot, is a skateboard, right? Because, well, we can't surf, but we still need to have an outdoor activity. So before migration, you would get a result like this. But now imagine what happens after the migration, and then our sales manager asks us the same question again, or we run this query again. Well, we would see something weird happen, right? We would see that a whole bunch of surfboards are appearing in Johannesburg because our customers updated their addresses. So now the customers who were in Cape Town are now in Johannesburg, and their product of choice was a surfboard. We suddenly see that a whole bunch of surfboards went to Johannesburg. And this leads us to a kind of weird analytical anomaly where we're kind of like saying like, wow, surfboards are really popular in Johannesburg, which is completely ridiculous, right? Because as I said, we're a landlocked city. There is no ocean near us. So this could lead us to some interesting insights, or we may suddenly want to run ad campaigns on all of our Johannesburg customers for surfboards, which is a really bad move, right? And we got this anomaly because there was an update and no history was preserved. Effectively, what had happened is that analytical integrity was broken while transactional integrity was preserved. And this is the key idea that I want to get across, right? Our third normal form database is really good at preserving that integrity where things are kept up to date in real time. But looking at data historically, we come up to weird anomalies happening over here. So what can we do about this, right? And how can we avoid this? Well, this is where analytical modeling comes in. I'm going to be discussing one technique, or a really common technique for analytical modeling, and this is fact dimension modeling. You may also hear this called Kimball modeling, named after Ralph Kimball, who really kind of formalized the ideas around fact dim modeling. You'd also hear about star schemas and snowflake schemas. Same idea, right? So this isn't the only analytical modeling technique out there, but in my experience, it's been the most popular, right? And it is pretty intuitive to work with. So this, I think, is really valuable to know. And really, I didn't come across this until I became a data engineer. I had never really heard about this, and I thought third normal form was the only type of modeling that existed. And if your data was not in third normal form, your database just sucked, right? So this was a bit of a culture shock to me, but has turned out to be really valuable to me as a data engineer. So to go through this at a super high level, fact dim modeling has a set of techniques to help us avoid these analytical anomalies. The premise really is to split our data into two categories: facts, which model measurement events. Personally, I like to think of these as the dependent variables in an experiment. So if you were to graph things, or imagine a graph, the y-axis is where we would put our facts. It is what we are measuring. And then dimensions, which model characteristics of events. And these are like independent variables. What would you put on the x-axis of a graph, right? These answer the kind of like who, what, why, and how type questions, or really like the what and how and who type questions, right? The why we'd have to answer using our analytical savvy. Another crucial point to note is that we can model dimensions or dimension type tables or entities to preserve history by favoring appends over updates. So one of the reasons our anomaly appeared with the kind of surfboard sales in Johannesburg is because we did an update directly on the data, but in fact dim modeling, we could favor appends over updates. We don't need to directly do an update. Instead, we could just append data onto our tables. So this is referred to, or these are referred to, as slowly changing dimensions. You may have come across this term. It's also abbreviated as SCD. So great, that's fact dimension modeling, like at a really high level. The theory can get quite in depth, but this is truly the key idea around it. Now, to design an analytical database, or kind of move our data from this transactional form into a more analytical compliant or analytically compliant form, the steps we'd go through, or the steps that I typically go through, are first identifying the process that we are modeling. Now, this one's super easy, right? We're modeling the sale of products to customers across different addresses. This is the process that we are dealing with. Then I'd go ahead and identify the facts. What is being measured in this process? And if you take a minute, think about that. What are we measuring in this process? Well, we are looking at the total value of sales, right? And the total quantity of sales. You could also include things like discounts over here. If our database is quite simple, we didn't mention discounts, but you could also look at discount amounts as something to measure as an example. So we've gotten our facts, right? Sales and quantity of sales. Then what we want to do is identify our dimensions. What are we measuring by in this process? So if you think through that for a second, what are the things we would like to use, or the aspects we would like to use to kind of divide up our facts? And really, in this case, there are about 4, right? There is product, address, customer, and then date as well, right? This is one that is often forgotten about, right? Or we don't really intuitively think about, but time, the most unforgiving dimension, needs to be modeled as well. So great, with these different kind of aspects in our minds, we can then move on to actually designing our analytical database, or our fact dimension database. As a quick note, in the kind of data warehousing toolkit book, which is the definitive guide, I'd say, that describes dimensional modeling, one of the steps is to identify the grain, and that comes on quite early in the process. So this just refers to how granular your data is. By that, I mean, what does a single row represent in the most detail possible? So in our case, it would be something like a sale per date, per customer, per address, per product, right? That's the most detailed view we can get. The reason I skipped over it is because it's a little counterintuitive if you're not familiar with this type of modeling, but it is a step that's quite valuable to look at. And if you do read through that book or come across some of the theory, you may come across the step of identifying the grain, brain. I just wanted to mention it over here so that you have it front of mind. But for our use case, which is quite simplistic, it's not super important to note. Alrighty, let us actually look at our ERD or entity relationship diagram for our new shiny analytical database. And this is what we would end up with, right? Or a proposition or a proposed form that I would suggest for us to use as a kind of dimensional model for our online retail store. So this may look a little weird at first, but we'll go through kind of each of the components step by step. But the first thing to note is the overall shape. Effectively, we have a fact table over here, which is capturing our quantity and amounts over here, is surrounded by dimension tables over here. And this is where that name star schema comes out of, because this kind of looks like a star over here. And if we had like a fifth kind of dimension around here, we could have a nicer looking kind of star schema, but that's why they are often called star schemas. You have these fact tables and dimension tables surrounding them. You also get a snowflake schema. This is where other dimension tables would filter or slice the kind of core dimension tables over here, but we're not really going to get into that. That's more of a, I want to say, advanced technique in dimensional modeling. And generally it adds a lot of complexity when you add kind of the snowflake idea to your schema. So you do typically want to avoid that as much as possible, but in some cases that's just unavoidable. However, we'll persist on. We've got a nice looking star schema over here. So the first thing to note is that we've denormalized the sales data into a single table. So no longer do we have sales order items and sales, I think we call them sales orders and sales order items. We have a single sales table that contains all that info at a very granular level. And to model the relationships, we've injected all the dimension foreign keys or their keys into the table, right? To kind of preserve the relationships between them. We've also added a date dimension over here. So previously we just recorded dates in our table, but we now have an entire table dedicated to dates. Why we do this is so that we can look at the kind of interesting aspects of a date and pre-compute those. By that, I mean, if you want to answer a question like how much was our sales or how many sales did we have in a quarter, you don't have to, as an analyst, go and sit and convert a date into the quarters and then aggregate your data. Instead, you just have the quarter available to you directly. A really interesting use case for this is looking at public holidays. So you can record which days are public holidays and you can answer interesting questions like, do my sales go up on public holidays? Do they decrease or do they kind of stay the same? It's also great to have this indicator here and you can kind of fulfill or update this in real time if public holiday dates change. Now, another interesting aspect to note and something surprising when you first come across fact-driven modeling is that we now have two IDs in some of our dimension tables. And this can look a bit weird to start with. So for example, in the address table over here, we now have an address SK, which stands for address surrogate key. Why we call it a surrogate key is because this is typically generated in your analytical database. So this is a brand new primary key given to your addresses, but we still store the original IDs for the addresses and refer to this as an NK or natural key. This is its natural key, and this is its new primary key that we use for our analytical model. Why we do that will become apparent on the next slide. I actually go through why we need surrogate keys and why we need these kind of funny ordered columns over here. So yeah, that was my next point, right? Is our dimensions have ordered columns. And these are the columns that I've represented in italics over here, the start date, end date, and is current type columns over here. These have been added or generated as part of our analytical database, and why those are important will become apparent. And then lastly, our fact to dimension relationships are many to one. So for example, again, if I use the address example, actually, if we look at the address, a single address can have zero or many, or appear zero many times in our sales fact. But a sales fact, when we look at something like the shipping address, can appear once and can have one and only one address for each kind of shipping value versus billing value over here. So you can have a different shipping and billing address, but if you look at them in isolation, there can only be one and only one address for each of our sales. right? And this is typical of a star schema. This kind of many-to-one fact-dim relationship is pretty common and makes things really convenient for us. So something else to note as well is that we've brought our dimensions closer to these facts over here, right? So now we have direct links between our dimensions and fact table, which also makes querying this a lot easier, right? When we have analytical type questions like we have about our different addresses to sales, we are pretty close in terms of proximity for querying. This makes our join logic a lot more tolerable, or a lot easier, should I say. All right, so moving on to why we've added these surrogate keys and why we have these kind of weird audit columns over here. So if we look at our address dimension table over here in a bit more detail, like if we took a subset of the data out of this, it would look something like this. We'd have our address surrogate key, our address ID, some other data, the city, the province or state, and then these audit columns of start date, end date, and is current. So in the very first example, you can see our surrogate key allocated over here that we generated as part of our analytical database is 1. Our original address ID with the natural key is also 1. And it turns out that the city over here is Johannesburg. The province where Johannesburg is Gauteng. And our audit columns over here for start date to end date. The start date is that this customer entered this value in on the 18th of September of this year. And there is no end date because this end date represents when this record or this value for the record was outdated or changed, right? So this turns out to be the current value. So in this first example, this is the one and only value we got for this particular address. Now, things are a little different for the second example over here, where we have a surrogate key of 2, a natural key of 2, and we can see this was originally someone's address in Cape Town in the Western Cape. But we can see that this has got a start date, but also an end date, all right? And it is no longer the current value for the record. It is no longer the most recent value for the record, as indicated by this is current is false. The next row in our table has a surrogate key of 3, so this has changed, right, and is a unique identifier. But we can see that this is still address ID with a natural key of 2, so this is where one of those updates happened when someone moved from Cape Town to Johannesburg. And we can see this person is now in Johannesburg, Gauteng, and this happened on the 19th of September, and this is the most current version of the record. The important thing to note here is that the surrogate keys are keeping track of different versions of the records, right? These surrogate keys indicate unique values over here, and in combination with the natural keys, keep track of different versions of our records over time, right? So we're not updating and forgetting what the previous value was. We are instead appending a whole new record onto the table to indicate the change. So in this case, where someone has moved from Cape Town to Johannesburg, we are recording that between these dates, they had their address as set in Cape Town. But now from this date onward, their address is set in Johannesburg. So we're almost versioning our different records. And then lastly, the audit columns keep track of when a version changed and which record is the most recent. Now, traditionally for this, you would actually just have the start date and end date, but this is current indicator is a nice touch to add to your dimensional model. Why? Is because it makes it super easy for an analyst or a data scientist or a data engineer, whoever is using your analytical database, to filter for the most recent version of a record. You can think about like the different analytical questions that come up or representations of the data that come up. It's pretty common for folks to want to know what is the most current version of a record, not necessarily the history. But of course, when we do want to answer questions across the history of the dimensions, we have that data available to us. All right, so going back to our sales manager's question now, using our analytical database, we could write a query like this, very similar in the beginning to how we answer this question using our transactional database. We've got city, product, quantity, and a total amount over here. But we have got we're using our sales fact table, joining this with our product, and then our address table over here, still doing our group and order by. But the thing is, we only had to do 2 joins this time, right? So our join logic was simpler. And you can imagine how this would reduce down your join logic for more complicated transactional databases. Like if you had a way more complex OLTP database and remodeled it into an analytical database like this using dimensional modeling, you would have significantly less joins, right? If you had way more tables in your OLTP database to get from one entity to another to answer a question, you'd have to do way more joins. But with a star schema, you have significantly less joins. And that's because of how close we've kind of put our dimensions to our facts. And most importantly, we get a consistent answer irrespective of updates on the transactional database, because our surrogate keys, I should say, in combination with our natural keys, keep track of versions over time. So we get an idempotent result. Idempotency is just a fancy way of saying that if I run my analysis query on Tuesday, I should get the same result on the next Tuesday, right? It's basically that when I give 2 inputs, or I give inputs into a function or process, I should get the same result every time. So same inputs, same outputs, always. And this is the result we are looking for when we are trying to preserve analytical integrity. So irrespective of whether or not someone has moved from Cape Town to Johannesburg, this is recording that when they were in Cape Town, they bought surfboards most commonly, and we don't have to care that they've made an update to their address. To round things out, the last thing I wanted to touch on is moving from transactional to analytical. So we've gone through these 2 different types of models that we have, this kind of idea of OLTP versus OLAP, but how do we move, or how is data typically moved from an OLTP kind of setting into our analytical kind of database settings, right? So at a super high level, and this is just a really high level discussion, things are obviously more complex in real life, but this is just a really simple model to go through to get the idea across of how we would move from our OLTP kind of databases to our OLAP databases. And we'd start off with our production applications, right? So maybe it's our website for our online retail store. And this would do real-time CRUD operations, CRUD standing for create, read, update, and delete type operations in real time. And we'd have our transactional or OLTP database keeping track of those operations. But we would have a data lake over here. And if you haven't come across the term data lake before, it's effectively just a giant file share service, usually on commodity kind of storage. So technologies like AWS S3, that's pretty cheap to store data in, you would use as a data lake. And what you do is take typically daily snapshots of transactional data. It doesn't have to be daily, it can be at a higher or even lower frequency than that, but usually you deal with daily kind of reports or daily snapshots of data, right? This is just what I've come across in my career, is typically we want daily freshness or kind of like daily periodicity in our data. And this gets snapshotted into our data lake and stored there. Then from our data lake, we'd move on to kind of a master data management system, or usually kind of move on to a master data management system. Why we would need an MDM is because you actually have many production applications over here, and you can imagine each production application having its own kind of set of customers associated with it, or its own set of transactions associated with it. In an MDM system, you want to bring all of that together. So if you have different business units, right, or different kind of like sub businesses within your big business, you want to bring together the data from all those different business units to answer questions like, well, how many total customers do I have, right? Or how many sales do I have in total across my different business units? Then we would move on to kind of OLAP stores. This is typically used by different teams of like analysts and data scientists. You'd have many, or could have many, OLAP stores branching off of your master data management systems. This is just for separate teams within the business who are interested in kind of separate items, right? They may be overwhelmed by your MDM. There just might be too much data to kind of like shuffle through. So you instead want to break this up into kind of sub OLAP stores. And then lastly, you have your kind of like BI applications. You could also have your data science applications sitting on top of your OLAP stores over here. Now, this is just as I say, like an oversimplified version of what goes on. You typically have like many production applications, many transactional stores. You can even have many data lakes in a business, right? And you preferably want to have just one master data management store. I mean, hence the term kind of master data, right? But you can sometimes find in organizations that there are like many master data initiatives happening in the organization. You've got to resolve that. Yeah, it can get messy really quickly. But this is just to give you an idea of the different components or common components out there. I mean, there are also things like feature stores that are gaining in popularity for data scientists. So like instead of a typical OLAP store, you want to store your kind of data sciencey features in their own database. These kinds of things crop up. But this is just like I want to say generic flow to give you an idea of how to move from transactional to analytical. And as a last remark, really, this is where we want to apply our factor modeling at the kind of master data management level or our OLAP store management, or both, basically, right? Dimensional modeling is not the only kind of analytical modeling that exists, right? So wait, there's more. So I don't want to kind of give you the idea that the only way to model analytical data is via dimensional modeling. It just so happens to be quite a popular technique. But out in the wild, you might come across these terms. There is the kind of data vault over here, and the scale up top just represents the degree of normalization. Now, data vault is pretty popular, and I've heard about it in several books that I've read, but I've never really come across a data vault implemented at a customer before, so I haven't really worked with a data vault before. But this is heavily normalized. Effectively, this is going up to like your 4th, 5th, 6th level of normal forms, and is a pretty strict idea of how you should model your data, but works really nicely in theory. Then we've discussed briefly over here our third normal form type of data modeling. This is used for our transactional kind of applications or our kind of production applications talk to third normal form databases. This is the usual like standard that's used for OLTP databases. We've also discussed like pretty in depth what dimensional modeling is, aka Kimball modeling, aka FactDim, aka star schema. And then interestingly, we have one big table modeling as well. And this is exactly what it sounds like. You are effectively putting all your data in a single big table. The catch, right, is that the one big table model uses complex data types to model many-to-many and one-to-many relationships. Typically, you're using things like arrays or hash maps, or aka dictionaries, to model the data. And this breaks even first normal form, right? Because no longer do you have atomic elements, you actually have like lists and sets and that kind of thing sitting as an element in your data model, right? Now you may ask, why would I want to do something like that? Isn't, denormalization bad? Well, it turns out that for really big data, like, I mean, huge, like petabyte scale data, one big table turns out to be more efficient. And why that is because you don't have to do joins, right? Because you've just got one big table. You don't have to do the join operation. And it turns out that join operations are pretty expensive, especially when you're going across a lot of data. So this is typically reserved for kind of petabyte scale data. There's also a lot of like other aspects you need to consider when moving to one big table, but it is interesting to note. Alrighty, so this brings us to kind of the end of the discussion. So just to give you a brief summary of what we went through, analytical databases exist to cater for low frequency, high data volume type queries. This is a key point. This is why we care about analytical databases, or kind of the key selling point of analytical databases. Lots of data, but at a low frequency. Then we also discussed why we can't use the typical relational model to cater for analytical use cases. You kind of run into weird anomalies, or weird anomalies can crop up if you're just using third normal form, or you're just applying your analytical queries to a third normal form database. This is more reserved for transactional integrity rather than analytical integrity. And then lastly, fact-dim modeling creates a simpler data structure for us to work with as data analysts, data scientists, and data engineers, and also preserves record history to cater for our analytics use cases or preserve analytical integrity. So this brings us to the end of our discussion. If you found this content valuable or helpful in any way, please do consider giving it a like and subscribing to the channel for more insights into data engineering, data science, and data analysis. And if you enjoyed this video, you'll probably enjoy my other videos. And I just wanted to say thank you so much for watching again, and I'll see you soon.